All right, the next thing I want to do is to talk about what are called inner products. So one of the things that mathematicians do is we take the idea, in this case, we're taking the idea of the dot product, and we want to see how far we can push it. So one of the first things to do is to kind of think about what are the different properties that the dot product has. And so let's notice that if I take two vectors, say x and y in Rn, and I compute the dot product and think about all the properties, we get the following list of properties. So one is that the dot product is what's called commutative. So what that means is that the order of the dot product doesn't matter. So the dot product of x and y is the same as the dot product of y and x. Okay, so the order doesn't matter. So you get commutativity. So this is called commutative. Can't spell. Can't spell today. Can't spell any day, but I also can't spell today. So commutative. We get, there's a distributive property. So if you were to take the dot product of y plus z, this would be the dot product of x and y plus the dot product of x and z. And so you got this distributive property. There's an associative property. Let me write distributive before I forget to. There's an associative property, which says that if I were to take a constant and multiply by the dot product of x and y, that's the same as taking the scaled vector k times x and dotting it with y. And that's the same as taking x and dotting it with k times y. Right, so there's this associativity property. And then finally, there's a non-negativity property. And so that says that if you take any vector and dot it with itself, remember what we get is you get the length of the vector squared. But in particular, this is greater than or equal to 0. And the only vector with 0 length is the 0 vector. So only if x is the 0 vector itself. So if you have these four properties for the dot product and you want to generalize the dot product, you should look for things that have these four properties. And so that's exactly what an inner product is. So an inner product. So what we're going to do is we're going to change the vector space. Okay, so we're going to talk about arbitrary vector spaces, which we've done now in chapter 4. And instead of talking about the dot product can be kind of our canonical example, but instead of talking about the dot product, we'll talk about an inner product. So an inner product on a vector space V is a function. So I'm going to write this kind of in a strange way here. But the way what we use is we use these angled brackets for a dot product. I put dots there so that if you want to write u and v, that's fine. But the idea here is that this is going to be a function. It's going to take pairs of vectors and it's going to return them to scalars, right? So you have a vector space V over a scalar set, typically R. And so the inputs of this inner product are going to be pairs of vectors and the outputs are going to be scalars. And so the idea here is that to be an inner product, you need four properties. The first is that if you have vectors x and y and v, I'm going to stop writing the arrow over them, but if you have vectors x and y and v, then the inner product of x and y is the same as the inner product of y and x. So that's commutativity. You have a distributive property. If you want to talk about the inner product of x with y plus z, that's the inner product of x and y plus the inner product of x and z. So that's kind of like a distributive property. And if you were to have a constant times the inner product of x and y, you could put the constant in the first spot or the second spot. Okay. Here, there's a little bit of an asterisk here. We've basically only talked about vector spaces over the reals. If you talk about a vector space over the complex numbers, this third item gets a little bit more complicated, but for real values, this is how it works. Okay. And then the final thing here is that if you take the inner product of a vector with itself, it should always be greater than or equal to 0. And it should only ever be 0 only if x is equal to the 0 vector in V, whatever that is. Okay, so if we're talking about a vector space of polynomials, we're talking about the 0 function. If we're talking about a vector space of matrices, we're talking about the 0 matrix. If we're talking about a vector space of Rn, we're talking about the 0 vector, right? 0, 0, 0. Anyways, so all of these 4 properties define what's called an inner product on a vector space. And then once you have an inner product, if I take this inner product together with the vector space V itself, we get what's called an inner product space. So an inner product space is a vector space together with this inner product with all these properties. And so let's talk about some examples. And kind of the first example is when we have our vector space, which is Rn, and 2 vectors, they're dot product, right? If that's an example of an inner product, of course, that's what we're basing everything off of. I want to point out there's a potential for just a slight amount of confusion here. I'm using these angled brackets in 2 different ways. Before, when we were talking about vectors in Rn, I used these to denote the vectors themselves, right? So the entries were real numbers. Here, we use these angled brackets to talk about inner products, one example of which is the dot product. Okay, so just depending on the context, if the inputs in the angled brackets are themselves vectors, then we're talking about an inner product. Otherwise, if the entries are just real numbers, then we're talking about the vectors in R2 and R3, like we're used to doing in calculus. So that's an example of an inner product space. You could talk about, for example, the vector space of, say, the continuous functions over the interval from 0 to 1. That would be an example of an infinite dimensional vector space. And here, the vectors, if you want to think about them, are the continuous functions f and g. And you could define, for example, lots of inner products, but one of which could be, say, the integral of f times g from 0 to 1. Okay, so that would be an example of an inner product. If you were to take another kind of common example here is if you were to take the set of polynomials of degree n and less, and here your inner product could be the integral from -1 to 1. So there's good reasons why you'd want to include the integral from -1 to 1 here. Okay, but that's an example. We could talk about if I were to have Rn, you could say that one way here is that if x and y are the vectors, so if x is the vector x1, x2, all the way out to xn, then of course the dot product is going to be an inner product, so y1, y2, all the way out to yn, but also any weighted dot product will be an inner product. So what I mean by that is that I can take any non-negative values that I want, say 5, x1, y1, plus 2, x2, y2, plus whatever I want, all the way up to 3, xn, yn. So here, the weights are 5, 2, whatever comes in between, and 3. And I'm not saying when I say dot, 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 I don't mean there's a pattern. I'm saying just whatever those numbers happen to be. So you can put whatever numbers you want here as long as they're non-negative. Okay. And actually they can't all be, they can't be 0. They need to be positive. Okay. So not only do they need to be not negative, they also can't be 0. So they need to be positive. So those are the weights. Okay. So you can talk about a weighted vector space. You can talk about the vector space where you're talking about n by n matrices. And here your vectors are matrices themselves. And what you could do is you could say that the inner product is going to be the trace of B transpose times A. And so if you actually do out what this is, if you actually like write this out and compute what is B transpose times A when you take the trace of it, it turns out what happens is that if A is this matrix A11, A12, A1n, like usual, A21, A22, all the way up to ANN. Here I'm just using square. You don't even have to have square here. You can have, yeah, any matrix that you want there. Anyways, AN1, AN2, all the way up to ANN. And likewise for B, let's just write B like this. So this is Bij, where I and j go from 1 to n. Then the trace of B transpose times A, it turns out, is going to be exactly very similar to the dot product. You're going to take the product of corresponding entries in the matrices. So A11 times B11 plus A12 B12 plus A1n B1n, and then for the next row and the next row and the next row. And so it turns out what you get is the sum of the values Aij, Bij, is I and j go from 1 to n. Okay, so you just take the products of corresponding entries in the matrices, and then you add them up. Okay, so it's very much like if you were to have, I think it's worth seeing the connection here with the dot product. If you were to have a matrix, say 1, 2, 4 or something. So let's say that's your A, and then B is going to be 2, 3, -1. Then the inner product of A and B with this inner product, okay, here I'm not talking about square matrices anymore, it doesn't matter. But here the inner product would be 1 times 2 plus 2 times 3 plus 4 times -1. And that should feel very much like the dot product, right? It basically is the dot product. When you're talking about, if you think of vectors as being n by 1 matrices or 1 by n matrices, the dot product is really just exactly this. So this is kind of a generalization of the dot product. And one other thing that I think is useful to say here is that when you do the dot product, you can think of the dot product as kind of, if I were to take B transpose times A, that would be 2, 3, -1 times 1, 2, 4. And so here I'm just thinking of standard matrix multiplication. I get 2 times 1 plus 3 times 2 plus -1 times 4. And so you get a 1 by 1 matrix because this is 1 by 3 and 3 by 1. So their product is 1 by 1. And 1 by 1 matrices you can just identify with real numbers. So there's no point in writing brackets around it. So this is basically what's happening here. Okay. And in general, if you were to have bigger matrices, you would want to talk about the trace in order to get that. But if you have just a 1 by 1 matrix, the trace is just 4. That's right. It's just the sum of that only entry in there. A few other things that I think are worth mentioning here, and one thing that I maybe should have explained earlier, is that the dot product is a generalization of just standard real number multiplication. So what I mean by that is that if I go back to the dot product and I think about, say, 1, 2, 3 dotted with 3, 1, 4, we know how to do this. We get 1 times 3 plus 2 times 1 plus 3 times 4, right? So we get 17. Okay, and so that's the dot product. But think about what would happen if, I mean, the real numbers themselves are a vector space over the real numbers. And so let's think about what would happen if I have, say, 4 dotted with, I don't know, 7. Okay, if I think of these as vectors themselves, they're kind of boring vectors. They're just real numbers. But it turns out that you get exactly what you think. You get 4 times 7. And so the dot product in a certain way is a generalization of just kind of standard multiplication. And the dot product on the matrices is kind of a generalization of the dot product. The inner product on the matrices, I should say, is a generalization of the dot product, which is a generalization of matrix with a real multiplication. So all of these things kind of fit in the hierarchy here, and they're all, in a certain sense, all the same thing. Okay, so the dot product again is just a way to generalize real number multiplication. Inner products are a way to generalize the dot product. So for what it's worth there. I think these are kind of all of the main dot products I wanted to talk about. You can do these weighted ones. If you want to talk about, there's of course lots of ways to define a dot product. So for example, an inner product, I mean, if you want to take, for example, V being the polynomials of degree n or less, you can take, say, let's just do an actual example here. Let's say V is P2. And so if you were to take, say, ax, let's say a1x squared plus b1x plus c1 dotted with a2x squared plus c2x, no, b2x plus c2. One other inner product that you can do is instead of multiplying them and then integrating the product, you can just take, say, the dot product of the coefficient vectors, right? So you could take a1, a2 plus b1, b2 plus c1, c2. So again, kind of a boring inner product, but that's another way that you could define an inner product of polynomials. It doesn't always have to be with integration or anything like that. So that is what it is. Now, once we have this notion of inner product, this whole world is kind of open to us now. We can talk about things like the length of a vector. We can talk about things like what's the angle between two vectors. We can talk about Gram-Schmidt. We can talk about orthonormal vectors and orthogonal vectors and orthonormal bases for inner product spaces, right? We can do all of this stuff once we have this notion of an inner product. And so what I want to do is just a little bit of this. If I take two vectors, so two vectors, let's say u and v, in an inner product space, they're going to be said to be orthogonal if and only if the inner product is 0. So that's the, not the 0 vector, just 0, the number 0. So that's what it means for two vectors to be orthogonal to each other. So here we no longer have the geometric intuition that we did with vectors in R2 and R3, but we can still talk about orthogonal vectors in the sense that their inner product would be 0. And we can talk about the length of a vector. So from now on, just to be completely, to write this as clearly as I can, the length of a vector u, I'm going to write with 2 lines. And so before, in the previous videos on this, I took the length of a vector in Rn and I wrote it with absolute value bars, just a single line on either side. I'm going to use 2 now to talk about the fact that the length of a vector in an inner product space is a little bit more general than just the length of an actual vector in Rn. So here I'm going to use 2 lines to denote the length of a vector, but it's going to be defined the same way as before. It's going to be the square root of the inner product of the vector with itself. And notice that this inner product is always going to be greater than or equal to 0, because it's one of the properties of an inner product. And therefore, we can take the square root of it. Everything is fine. That's how we're going to define the length of a vector u. And finally, we can talk about the angle between the two vectors. So between is kind of not the right word anymore, but we still use it. The angle between u and v is still going to satisfy cosine of theta, where that's going to equal the inner product of u and v divided by the length of u times the length of v. Okay, and so that's going to be how we find the angle between arbitrary vectors. Okay, and all of the stuff that we've done up to this point is completely generalizable to arbitrary inner products. So just as an example, if I wanted to find the angle between, say, x and x squared, where we're thinking of the vectors here as being the, say, the polynomials. It actually doesn't matter whether the vector space is the polynomials or the continuous functions. And what really matters is what the inner product is. So the inner product is going to be the integral from 0 to 1 of f times g. The angle between them we can compute by looking at this formula. So cosine, whatever this angle is going to be, we'll figure it out in a second. But cosine of theta is going to be the inner product of f with g. So that's going to be the integral of x times x squared. That's going to be 1/4. Here I'm just using, this is just a common trick I want to just point out. This is probably pretty obvious here, but if I integrate from 0 to 1, then the integral of x to the k from 0 to 1 is going to be 1 over k plus 1, as long as k is non-negative, right? As long as k is greater than or equal to 0, everything's fine. So this is going to be 1 over k plus 1. So we get x times x squared is x cubed. The integral from 0 to 1 is going to be 1/4. And let's see, the length of the vector f and the length of the vector g. So the length of the vector f is going to be the square root of the integral of x times x. So that's going to be 1/3. So we'll get 1 over square root of 3. And the length of the vector g is going to be 1 over square root of 5. So it's going to be x squared times x squared is x to the 4th. So we get 1/5. And so all together, what's going to happen here is we're going to get, this is going to be square root of 15 over 16. And therefore, theta is going to be inverse sine of square root of 15 over, I don't know why I wrote 16, square root of 15 over 4, 16 outside of the, I could write it, so I could write it, it's probably obvious what I was thinking here, but I could write this as square root of 15 over 16 or square root of 15 over 4. I don't know why I brought 16 into it at all. But anyways, if you compute arc cos of square root of 15 over 4, we just have to plug this into a calculator here. And it turns out that what we're going to get is about 0.25 radians. So 0.25268 radians. Okay, so something like, I don't know, pi over 12 or something. I don't know exactly what it is. But that's about what it is. Okay, so that's how we can find the angle between the two vectors, even though there's no geometry in here at all, right? We're still talking about cosine of theta with the same formulas. Everything works exactly the same. We're just replacing all of the dot products with inner products. And we can also do this with the projection, right? If I talk about the projection of V on U, remember that this is going to be U dotted with V over U dot U times U. Okay, and so here, what we're going to do is we're going to do the same thing. We're just going to replace all the dot products with inner products. So we get the inner product of U and V divided by the inner product of U and U times U, right? So we can still make sense of the projection. And once we have the projection, we can still make sense of Gram-Schmidt. Okay, so we'll go through and we will talk about Gram-Schmidt for vector spaces other than Rn themselves. But before we do that, the last thing I want to do before we go through and do Gram-Schmidt is I want to talk about, there's just a little bit of stuff here to talk about. So let's talk about what's called Cauchy-Schwarz. So Cauchy-Schwarz basically says that since we have this angle, cosine of theta is the inner product over the lengths of the products. What this kind of implies, and this is slightly backwards actually, the fact that Cauchy-Schwarz is true means that we can write cosine of theta like this. But the point here is that the magnitude of x times y is going to be less than or equal to the length of x times the length of y. And the Cauchy-Schwarz inequality, or the Cauchy-Bunyakovsky-Schwarz inequality, there's, again, naming things is tricky business in math, but there's a third mathematician named Bunyakovsky who for some reason doesn't get his name attached to this, but I'm just as guilty as everybody else apparently, because I'm going to call it Cauchy-Schwarz. The Cauchy-Schwarz inequality here is one of the most ubiquitous and one of the most useful inequalities in all of math. It gets used absolutely everywhere. I can almost guarantee you've already seen it in a Calc 2 context. We just didn't necessarily call it Cauchy-Schwarz. So if you wanted to think about it, for example, Cauchy-Schwarz, if you think about the dot product, Cauchy-Schwarz says that x times y is going to be less than or equal to x squared over 2 plus y squared over 2. Okay, so this is kind of the elementary version of Cauchy-Schwarz. You can kind of talk about this without talking about any inner products or vector spaces at all, of course, but Cauchy-Schwarz is a super, super useful inequality. And it turns out that since this inequality holds, well, that tells you that the inner product of x and y is always, well, the inner product of x and y divided by the length of x times the length of y is always between -1 and 1. And therefore, you can talk about cosine of theta being equal to this quantity. So anyways, the fact that Cauchy-Schwarz holds means that you could still make sense of the angle between vectors. So that's kind of what lets you do that. So that's what's the Cauchy-Schwarz inequality there. Cauchy-Schwarz for sums, for example, if you were to look at, say, a sum of ai times bi, where I goes from 1 to n, it turns out that this is going to follow this pattern. So it's going to be the sum of a sub I squared as I goes from 1 to n times the sum of b sub I squared as I goes from 1 to n. Okay. And if you don't like the square over here, that's fine. That's no problem. You can just take the square root of both sides. Okay, and so that's Cauchy-Schwarz inequality. That's exactly what this says when the inner product is the dot product itself for vectors in Rn, right? Because if you think about the length of the vector in Rn, what is that other than the square root of the sum of the components? So you have the square root of the sum of the squares of the components, right? And so anyways, this is Cauchy-Schwarz. This ends up holding for all inner products. One other thing that's useful here is the triangle inequality. The triangle inequality says that if you have an inner product space, you can make sense of the length of a vector by taking the square root of the inner product of a vector with itself. And the length of a vector satisfies the inequality that u plus v is always less than or equal to the length of u plus the length of v. Okay, so that's what's called the triangle inequality. And when u and v are actually vectors, you can see why it's called the triangle inequality. You have a vector u, you have a vector v, and then the vector u plus v, what you do is you kind of take this vector u and you put it tip to tail. And you think about what's the new vector that you've drawn here. So this red vector is u plus v, where this is u and this is v. And so the length of u plus v is always going to be less than the length of u plus the length of v. This basically says that if you have any triangle, the length of one side is going to be less than or equal to the sum of the lengths of the other sides. And interestingly, in a triangle situation, you get that there's certain cases where you have equality, right? If you have vectors like this, then if these vectors are orthogonal, then you get equality. It's not just less than or equal to, it's actually equal to. And what do we call that? Well, that's the famous Pythagorean theorem. And there's a Pythagorean theorem here as well. If u and v are orthogonal, then it turns out that you get equality in the triangle inequality. So you get that the norm of u plus v is the norm of u plus the norm of v. Okay, so that's the Pythagorean theorem in this context. And again, if we revert back to kind of thinking about this in terms of vectors, that's the original Pythagorean theorem, or you could think about it as side lengths of triangles, which is how Pythagoras thought about it. Okay, so that's the Pythagorean theorem, the triangle inequality, and Cauchy-Schwarz. Okay, and so that's basically everything I wanted to say so far here. So in our next video, in our final video on this topic, what we'll do is we'll do an example of Gram-Schmidt. We'll talk about orthogonal complements. We'll talk about finding orthonormal bases for various vector spaces. Okay, so we'll do that in the next video.